Okay, so as we turn to this series here, uh, k goes from 1 to infinity, e to the minus 2k. You might look at that and say to yourself, that doesn't look like the geometric series things we've just been doing, right? That had something just to the k, but now you have this minus 2k as the exponent. Well, let's just first start writing off the terms. For one thing, we have a problem with it being starting at 1 instead of 0. That's a problem anyway. So let's just see what this looks like. First few terms. So plug in 1, that would be minus 2 times 1. So this would just be e to the minus second. Plus, plug in 2, be e to the minus fourth. Plug in 3, be e to the minus sixth. Plug in 4, be e to the minus eighth. And so on and so on. Okay, so now you can see that this actually does fit the pattern of a geometric series, even though that's set up with the 2k exponent instead of just a k might have thrown you off at first. And then to work this out, we use the same idea I showed you in the last one, which is take the first thing you have there and notice that that's a common factor of everything else. So we're going to factor out an e to the minus second. We're going to factor out an e to the minus second. When we take that out of the first one, it'll be 1. When we take it out of the next one, that'll be e to the minus second. Take it out of the next one, that'll be e to the minus fourth. And then e to the minus sixth. And so on forever. Okay, so you can see how this is now definitely fitting the pattern of a geometric series. Now I'm going to clean it up just a little bit and write that as 1 over e squared on the outside, and then realize that each one of these is 1 over e squared. The next one is 1 over e squared squared. The next one is 1 over e squared cubed, and so on. So it turns out we're dealing with a geometric series where a is 1 over e squared, and the ratio is also 1 over e squared. Okay. So now we can express this in terms of a geometric series starting at 0. So this is the sum as k goes from 0 to infinity of 1 over e squared times 1 over e squared raised to the k power. And now we can just use our formula for the geometric series. So that's going to be a 1 over e squared on top divided by 1 minus 1 over e squared. And now here I am going to leverage my complex fraction idea here and multiply both top and bottom by my common denominator of e squared, so that in the end I get 1 on the top divided by e squared minus 1. And so, of course, if we needed to approximate that, we could do so on a calculator. E, again, is just that natural exponential. So 1 divided by e to the second minus 1. And so there it is, the decimal 0.1565, and so on. Okay. But I'll just leave it in its exact form here with e, since we could easily do that on the calculator if we needed to.